Hello class. So we're still in chapter 15 here. We're going to talk about the reaction quotient, which is labeled with a capital Q. It's actually very similar to the equilibrium constant. The difference is that this is used at the beginning of a reaction to tell which way the reaction will go. Again, a capital QC for molar concentrations, or QP for partial pressures. Our Q, I was going to say Q, the reaction quotient, is used to determine which way a reaction will go. Okay? Kc and Kp are used at equilibrium, correct? So Q is used when you have your initial conditions. And this is, again, I told you, it's very similar to Kp, Kc, right? If we take a general chemical equation, right, again, lowercase letters are stoichiometric coefficients, capital letters are chemical species. And you're going to write out the reaction quotient. It looks the same, actually. It looks the same as the equilibrium constant. So say we have QC. It's going to be reactants over products. Concentration, of capital C raised to the stoichiometric coefficient. Have a concentration of capital D raised to its stoichiometric coefficient divided by the reactants. Like thus. Again, products over reactants, just like the equilibrium constant, right? Again, the difference with this is that you use this to determine which way a reaction will go. It's not used at equilibrium. So to determine which way, actually, let me erase this, make some more room here on the board. Let me write this down. Q uses the initial concentrations of reactants and products. Okay, again, that's the difference between Q and K, the equilibrium constant. To determine which way a reaction will go, we will compare, K, the equilibrium constant, Kc or Kp, and Q, again, QC or QP, whichever one's relevant, okay? If Q equals K, the equilibrium constant, this means reactions at equilibrium. All right, pretty straightforward. If Q is less than K, the reaction will shift to the right towards products to equilibrium. To reach equilibrium, okay? If Q is greater than K, right, the reaction will shift to the left to reactants to reach equilibrium. Okay, let me write this again, right? I'm gonna keep that there, right? Let me rewrite my generic chemical equation, and let's look at this, what this means mathematically. Okay, so again, my general my Q switch those two around, but it doesn't matter. Products over reactants, right? So now, if Q equals K, the reaction's at equilibrium. So if these concentrations of products and reactants are the same as K, well then it's at equilibrium, that's the definition. If Q is less than K, the reaction will shift to the right, okay? So if Q is less than K, what does that mean? That means that your denominator is let me think of this here, in terms of reactant actually. That means if Q is less than K, that means our denominator is too large. What does that mean? That means that there's too many reactants, okay? If Q is less than K, that means the denominator is too large, okay? There's too many reactants. The reaction will shift right to products, okay? I hope I explained that so it makes sense. Either memorize this or be able to figure this out, right? Q greater than K, the reaction will shift towards the reactants. If Q is greater than K, what's going to happen? You can think of it as our numerator is too large, right? Our numerator is too large. We have too many products. We need to shift from products to reactants. That's why if Q is greater than K, the reaction will shift left to reactants, all right? So these problems are relatively straightforward. They're going to give you a chemical reaction, they're going to give you the initial concentrations, and then they're going to ask you to predict which way the reaction will go. And we'll look at an example here from our book. Let's take a look here. We'll do exercise 15.10. All right, and we're going to have this reaction. We're going to have H2 gas plus I2 gas goes reversibly to 2HI gas, all right? It tells us at 448 degrees Celsius, the equilibrium constant Kc for the reaction is 50.5 for this reaction. And then it says predict in which direction the reaction proceeds to reach equilibrium if we start, why do they always do this? If we start with 2.0 times 10 to the minus 2 moles of HI, 1.0 times 10 to the minus 2 moles of H2, and 3.0 times 10 to the minus 2 moles of I2 in a 2-liter container. So we're going to have to calculate the concentrations. So that's why it's a pain in the ass, right? But here's what we're going to do. I'm going to go like this. Starting off. Concentration of HI is going to equal the starting number of moles divided by our 2-liter container. And then that'll give us the molarity, right? Then we can use that to calculate Q, okay? What we're going to do, so I'm going to write out all these concentrations, right? We'll figure them out. And then we're going to calculate Q, which again, products over reactants. And we'll plug those numbers into here, and then we'll compare Q to Kc to determine which way the reaction goes. Right, let me finish this. Concentration of H2 is going to be 1.0 times 10 to the minus 2 moles divided by 2. And then concentration of I2 is going to be 3 times 10 to to the minus 2 moles divided by 2 liters. I don't know why they do this for this problem. Let's just make this straightforward. Right? Maybe I should have picked a different one, but this is an example in the book. So let's figure this out, right? So what are we going to have here? Well, we're going to get 1.0. 1.0 times 10 to the minus 2 molarity HI. Here we're going to get molarity H2. And then here we're going to get I2. So after that part, whatever, now this part's easy. We're going to take these numbers, we're going to plug them into here for Q, and then we're going to compare to Kc and see which way this reaction goes. So concentration, molarity of HI, 1.0 times 10 to the minus 2 molarity squared. Oops, I should put HI in there. Down here, molarity of H2, which is right there. Right? And then times the molarity of I2, which is right there. Plug all of that into your calculator. And it says here that this is 1.3. So what happened? Q is less than K. What did we say prior? If Q is less than K, that means that we need more products. So our reaction will shift to the right. Correct? I guess if there's any questions, you're going to have to email me, right? Let's continue on. So that was Q. Okay, again, Q is used to determine which way a reaction will go, right? I don't think this problem is too difficult. They made this more of a pain in the butt. You had to figure out the molarity. But basically, all you do is you calculate Q, which is written out the same way as the equilibrium constant, except you use initial concentrations, and then compare it to K, and determine which way the reaction will shift. Again, if you don't memorize these, Q less than K, look at your equation, right? If Q is less than K, again, what do you need then? If Q is less than K, that means that our denominator is going to be too large, right? Too large. So again, if the denominator is too large, which is the reactants, we need to shift to the products, okay? Making this smaller, right? So it'll increase the value of Q, and then it'll equal K eventually. Actually, I'm going to stop there and start up again in a moment.